September 1st, 1939. Nazi tanks roll into Poland. World War II begins. On the same day, a 35-year-old physicist at the University of California, Berkeley, quietly publishes 4 pages of mathematics in a journal called Physical Review. His name is J. Robert Oppenheimer. The paper describes something the entire scientific world, including Albert Einstein, says cannot exist. A star that collapses so completely, so totally, that it vanishes from the universe. No light escapes, no signal leaves, nothing. Einstein has already published his proof that this is impossible. Oppenheimer uses Einstein's own equations to prove him wrong. To understand what Oppenheimer proves, you need to understand one thing first. Every star in the sky is a tug of war. Gravity pulls inward. Radiation pressure pushes outward. These two forces balance each other. That balance is what makes a star a star. The Sun has been in this balance for 4.6 billion years. But stars run out of fuel. When the fuel runs out, the outward pressure dies. Gravity wins. The star begins to collapse under its own weight. The question physicists in the 1930s were asking is simple. Where does it stop? Everyone assumes it stops somewhere. In 1915, Albert Einstein published his general theory of relativity. It is the most precise description of gravity ever written. It describes gravity as the curvature of space-time itself. Mass bends space. Space tells matter how to move. In 1916, the German physicist Karl Schwarzschild solved Einstein's field equations for the simplest possible case, a single spherical non-rotating mass. He did this while serving at the front lines of World War I. His solution worked, but it contained something disturbing. At a specific radius around any mass, now called the Schwarzschild radius, the mathematics breaks. Some terms in the equations shoot off to infinity. The solution becomes singular. Physicists in 1916 did not know what to make of it. Most assumed it was a mathematical error, a ghost in the equations. They reasoned that nothing physical could actually reach the Schwarzschild radius. Nature would not allow it. Einstein agreed. In 1939, he published a formal paper in the Annals of Mathematics, arguing that the Schwarzschild singularity could not exist in physical reality. He concluded that stars would have to move faster than light to reach that point. Since nothing moves faster than light, the collapse stops before the singularity forms. The world's greatest physicist had spoken. The question was closed, or so everyone thought. Oppenheimer arrives at this problem from a different direction. He is not starting with singularities, he is starting with dead stars. Between October 1938 and July 1939, Oppenheimer publishes 3 papers in sequence. Each one builds on the last. Together they form a logical trap, and the universe is caught inside it. The first paper, written with Robert Serber, examines the properties of neutron stars. A neutron star forms when a dying star's core collapses past the white dwarf stage. Electrons get squeezed into protons. The protons become neutrons. The result is a ball of pure neutrons, roughly 20 kilometers across, with the mass of the Sun compressed into a space the size of a city. A teaspoon of neutron star material weighs approximately 1 billion tons. But before Oppenheimer can tackle neutron stars, he has to deal with white dwarfs. In 1930, a 19-year-old Indian physicist named Subrahmanyan Chandra Sekhar calculates the maximum mass a white dwarf can hold before its electron pressure fails. That limit is 1.44 times the mass of the Sun, the Chandra-Sekhar limit. Arthur Eddington, one of the most respected astronomers in the world, publicly ridicules Chandra-Sekhar. He calls the result physically absurd. He argues nature would never allow such a fate for a star. Chandra-Sekhar is right. Eddington is wrong. Chandra-Sekhar wins the Nobel Prize in 1983. When a star's mass exceeds the Chandra-Sekhar limit, electron pressure fails. The star collapses further. The next thing that can stop it is neutron pressure. This is where Oppenheimer's second paper enters. On massive neutron cores, Oppenheimer and his student George Volkoff applied general relativity and statistical mechanics to neutron stars. They calculate the maximum mass a neutron star can hold before neutron pressure also fails. Their answer is approximately 0.7 solar masses. This is now called the Tolman-Oppenheimer-Volkoff limit, or TOV limit. Modern estimates have refined this figure to between 2.1 and 2.9 solar masses, accounting for nuclear forces that Oppenheimer's 1939 calculation neglects. But the conclusion stands. Neutron stars have a ceiling. White dwarfs have a ceiling. Neutron stars have a ceiling. Every ceiling leads to the same question. What happens to a star too massive for either? Oppenheimer has one paper left to write. In the paper on continued gravitational contraction, published September 1st, 1939, J. Robert Oppenheimer and his graduate student Hartland Snyder do something no physicist has done before. They follow the mathematics all the way down. They construct a model, a perfectly spherical star, with no spin, no internal pressure, no mass loss, and no radiation. When the star exhausts its nuclear fuel, gravity takes over completely. The star falls inward. There is nothing to stop it. The model is simplified. Oppenheimer knows this. The simplification is deliberate. Strip everything away. Leave only gravity. See where it leads. What it leads to is this. The star collapses past the Schwarzschild radius. It does not slow down. It does not stop. It passes through what Einstein said was impassable. Now Oppenheimer and Snyder examine the collapse from two vantage points. The first observer rides on the surface of the collapsing star, falling inward with it. The second observer stands far away and watches. For the first observer, the collapse is quick. The star falls through the Schwarzschild radius in a matter of hours. Once the star's surface crosses that boundary, the cone through which any light signal can escape closes entirely. No message can leave. The observer on the surface passes through the event horizon without feeling anything unusual. Their clock ticks normally. They fall on toward the center. For the distant observer, the story is completely different. As the star approaches the Schwarzschild radius, light from its surface becomes redder and dimmer. The star's image slows. The collapse appears to decelerate. The star appears to freeze at the Schwarzschild radius, suspended in time, never quite disappearing. Two observers watch the same collapse. They see two completely different endings. Both are correct. This is not a contradiction. It is what general relativity actually predicts. Gravity stretches time. Near the Schwarzschild radius, time runs so slowly, from the outside observer's perspective, that the collapse appears to halt. The star closes itself off from the universe. Its gravitational field remains. Everything else is sealed inside. Oppenheimer and Snyder write this plainly in the paper, that the collapsing star tends to close itself off from any communication with a distant observer. Only its gravitational field persists. The first modern theoretical description of a black hole is written down in 4 pages of physical review. The term black hole will not exist for another 28 years. John Archibald Wheeler coins it in a lecture in New York City in the fall of 1967. But the object itself, Oppenheimer has already described it completely. The scientific world rejects the paper. Most physicists at the time simply cannot accept what the mathematics is showing them. Gravitational time dilation at this scale, a star effectively stopping in time from the perspective of a distant observer, is too extreme. The mental picture does not fit. Physicist Wolfgang Pauli doubts the event horizon is physically real. Others argue that real stars, messy, rotating and radiating, would behave differently from Oppenheimer's idealized model. They suggest the singularity is an artifact of the simplification, not a feature of nature. Even John Wheeler, who will later become one of the greatest champions of black hole physics, initially opposes the idea. Wheeler argues that there must be some physical mechanism that prevents complete collapse. He calls the concept philosophically repugnant. Lev Landau of Moscow goes further. He suggests modifying quantum mechanics itself to ensure unlimited collapse can never happen. The resistance is not ignorance. These are serious physicists raising serious objections. The problem is that the mathematics of general relativity at this scale requires an entirely new way of thinking about space, time, and the behavior of matter. The things the equations are producing have no analogue in everyday experience. There is no way to picture them intuitively. Kip Thorne, one of the leading relativists of the 20th century, later explains the reaction plainly. He says it was hard for people of that era to understand the paper because the things being smoked out of the mathematics were so different from any mental picture of how things should behave in the universe. Then World War II consumes physics entirely. Oppenheimer disappears into the Manhattan Project. The paper sits largely unread and dismissed for nearly 2 decades. But those simplifications do not hold the paper back forever. The objection that real stars behave differently from Oppenheimer's idealized model is put to rest by Sterling Colgate and his team at the Lawrence Livermore National Laboratory. Colgate's team adapts the same computer codes built to design the thermonuclear bomb and uses them to simulate the gravitational collapse of a real star. The star in the simulation is spherical, but otherwise modelled with full physical complexity, real pressure, real energy loss, real stellar structure. The result matches Oppenheimer. A sufficiently massive star undergoes continued gravitational contraction in exactly the manner Oppenheimer and Snyder describe. The simplifications do not change the conclusion. The idealized model and the real model converge at the same place Oppenheimer pointed to in 1939. Gravity, given enough mass and no pressure to oppose it, does not stop. The star collapses indefinitely. It seals itself away from the rest of the universe. A boundary forms, the event horizon. Inside that boundary, not even light escapes. The Schwarzschild singularity is not a ghost in the equations. It is a prediction. In 1965, Roger Penrose published 4 pages in Physical Review Letters titled Gravitational Collapse and Space-Time Singularities. He proved that singularities are not a byproduct of Oppenheimer's simplifications. They are a requirement of general relativity itself. Any sufficiently massive collapsing object, regardless of its shape, spin, or internal complexity, will form a singularity. The idealized model and the messy real universe lead to the same place. Penrose cites Oppenheimer and Snyder directly. In 1972, astronomers identified Cygnus X1, the first widely accepted black hole candidate. It was found by measuring the orbital motion of a visible companion star being pulled by something massive and invisible. The unseen object is too heavy to be a neutron star. It fits only one description. In 2020, Roger Penrose received the Nobel Prize in Physics for proving that black holes must form. The Nobel Committee traces the origin of the idea back to Oppenheimer's 1939 paper. Oppenheimer never received a Nobel Prize for this work. He died in 1967. That same year, John Wheeler named the thing Oppenheimer built. 4 pages, published on the first day of World War II, ignored for 20 years. The universe had been making black holes for billions of years before anyone believed in them.